Welcome everybody. The course is called Frontiers of Computational Journalism because it's a research level introduction to what are people doing with computers in journalism. And the first thing we're going to do is define a little bit closer what that means, a little bit more carefully, and show you some examples. And then today's lecture is called High Dimensional Data. So I imagine a lot of this will be familiar to a lot of you, but probably not all of it will be familiar to all of you. As we proceed through the course, I'll get a better sense of who's done already an NLP course or an ML course, or worked with high-dimensional data already. So this first course is really just sort of getting up to speed on a bunch of stuff, and then we're going to get into the TF-IDF model. Who's done that before in some form? Okay, yeah, so we're going to find that a lot, right? So about half of you have done something. And in particular, we're going to develop it, and then I'm going to show you how I used it in a piece of software called Overview, which is a document mining system used in investigative journalism. All right, so that's the plan. Questions so far? Great. So the first thing I want to talk about is what's the definition? What are we doing? So I pulled a few different definitions. I think this one is my favorite. This is the idea of sort of data mining, right? So we are using advanced computational techniques to find stories in data. Make hidden connections. There's all these sort of relatively vague ways of describing this. The purpose of this course is to make those concrete instead of vague. And this is mostly what I work on as well. But there are a bunch of other places where we use computer science and journalism that we'll talk about. So just as an example of what that first category looks like. So here's some documents that were obtained from the U.S. State Department through a Freedom of Information request about private security contractors in the Iraq War. When we talk about data mining, this is what some of this stuff looks like. So, do any of you remember this issue? It was a big issue about 10 years ago of private military contractors attacking Iraqi civilians during the war. In particular, there was one incident in a place in Baghdad called Nisour Square, where they ended up killing 17 civilians. And part of the issue is that the legal regime that the contractors were operating under was very unclear. They weren't U.S. military, so they weren't subject to court-martial, and they weren't subject to domestic Iraqi law as well, and they weren't subject to any American law. So basically there was no legal basis for punishing them for war crimes, which eventually got fixed. But anyways, it was a big deal and appeared at press conferences. And so we got these 4,500 pages, and not me, a guy named John Cook, who spent some time at Gawker and is now at Reason Magazine, filed this FOIA request. Took 3 years. Came in, this much paper, arrived on paper. Scanned it, put it online. He did a story on it, and then I did a story using some document mining techniques. And we'll talk a little bit about that later. Or this is another example of the sort of thing that we're talking about with this sort of data mining example. So this is a piece called Surgeon Scorecard. This is the first ever publication of surgical complication rates that name doctors. So Eugene Wolfe has done a knee replacement 83 times, and his complication rate's about 2%, with a fairly wide error bars. And this was a piece that was produced at ProPublica from 5 years of Medicare data. So Medicare doctors provide about 40% of the medical procedures in the United States. So it's a as big of a sample of medical data as you're going to get. And there were 70 million rows in the original data set. And so what we did is we screened for all of the elective procedures, and then we adjusted for patient characteristics to try to level the playing field in a number of ways. And we'll get into this when we talk about, when we do our class on regression. So this is the like classic data mining produces journalism type of thing. And this was very influential, by the way. The reason ProPublica did this was because best estimates are that there are about 200 to 400,000 deaths per year due to preventable medical error. It's one of the leading causes of death in the country. Patient safety advocates have been saying that transparency of surgical outcomes is one of the big things that might help. They've been saying it for 20 years. ProPublica did this. It was very controversial, but definitely advanced the conversation about transparency of outcomes. I worked on this. I did the statistical programming for it. We'll talk about this later. From the same paper as the first definition, there's this other definition which is even broader, right? So it talks about not just story production, but discovery, presentation, aggregation, monetization, right? So to me, when I look at this, I think, okay, so now we're talking about Google. Now we're talking about the Facebook newsfeed. And we will definitely talk about those things in this course. We will study the design of information filtering algorithms. That's actually basically the topic of the first third of the course. You will design your own algorithms. We're going to talk about filter bubbles. We're going to talk about all of the algorithms behind these things. We're going to talk about designing them so they serve social ends, because that is very much in the realm of what we talk about in the journalism school now, because it's such an important part of the public sphere. And a few past students have now gone on to do things like work on the Facebook newsfeed. So I'm training you not just to be a computational journalist working in a newsroom. I'm training you to be someone who builds the infrastructure of the public square. That's sort of the topic of this course. So what does that look like? This is an example within a newsroom. This is a talk by Shailesh Prakash at the Washington Post. It's at last year's Computation plus Journalism Symposium. And what this slide is it's describes their virality predictor. In other words, a story is published, you collect signals about the performance of that story for, let's say, 30 minutes, and you want to know if that story is going to be viral or not, right? So it's because you want to know to promote it more, right? If you know that a story is doing well, there are lots of things you can do. You can push it out on more channels to try to get even more traffic. You can think about your ad sales on that page and maybe even perform a real-time auction for those clicks. I don't know that they're doing that, but it's certainly a possibility. You can write more stories on that topic. All kinds of things, reasons you want to know this. And so this is actually some of the most advanced machine learning models in journalism. Tend to be on the business side. So we're going to talk a little bit about that, a bit less about that, in part because I feel that's pretty well covered in other places. This doesn't look that different from sort of business analytics, data science stuff in general. But there's a lot of it. This is another example of using computer science techniques to do something in the public sphere that isn't producing stories. So we're going to have a whole class on tracking effects. This was a map of the spread of the Coney 2012 video, which, how many of you remember this video? Yeah, okay. So at the time, it was the fastest viral spread of any video ever, and perhaps anything ever. And so Gilad Lotan mapped the network, the Twitter network of the distribution to sort of see who the major nodes were. the point I'm trying to make by including this is that the system we're going to look at spans this entire chain from story production all the way through distribution, and then after distribution too. You can look at the effects of a story. And then it cycles, right? It's actually not just a linear chain, it's a loop, because the story has some effects that changes the world. We re-report on the world. So we're in this constant feedback system, and there is code everywhere in that feedback system now. The other major theme of this course is algorithmic accountability, which is what we call it in journalism, but the idea appears in a lot of fields. It's the idea that algorithms have power. They're being used for making credit decisions, hiring decisions, decisions about who goes to jail. We're going to talk about that at great length. All kinds of stuff. And so part of keeping tabs on the power in society is keeping tabs on what algorithms are being used and how they work. And this is something which only people with computer science background can really do, at least at the level of asking how the algorithms work. The stuff around the algorithms turns out to be very important as well. But that's no excuse for not knowing how the algorithms work. So we're going to start looking at reverse engineering this stuff. By the way, you'll all get these slides, so don't worry about that. So as an example of what that looks like, here's one of my favorite examples of algorithmic accountability. This is looking at how prices vary by zip code for Staples, which is an online office supply retailer. And it found that basically things were more expensive away from urban centers. And we're going to talk about this particular example and a bunch of other examples, right? So one of the questions you can ask here is why, right? And the short answer is, well, it makes them more money, but there's a more complicated answer, which is sort of, well, how did they get to this? Was there a human who was sitting there optimizing things? Were they running an algorithm to optimize sales, which is what I believe happened? If so, what did the algorithm look like? We'll hypothesize about what the structure of that algorithm was. And then there's the effects, which is that generally higher income correlates to population density, meaning that people are richer in the cities, meaning that they are charging poorer people more for the same product. Right? So that has obvious social implications. And then, start expanding that out times millions for every company. These pricing algorithms start to have serious implications for the structure of capitalism. And algorithms appear in finance. We're going to be talking about that quite a lot as well. Here's another sort of algorithmic accountability story. This is ProPublica's message machine, which is an attempt to reverse engineer political micro-targeting in the 2012 election. I don't think they did this in 2016. That sort of had a different set of approaches. But what they did is they collected a bunch of emails, clustered all of the similar ones using TF-IDF. So by the end of this class, you'll know how they did that. And use that and collected demographic information. Use that to try to figure out who got what email. So how did the Obama and Romney campaigns target people? And of course, in a post-Cambridge Analytica world, political micro-targeting is now very much in the spotlight. So these are the kinds of things we do, right? And so you can think of it as basically two directions. One is you use computation to say or discover things about society, and the other is you do journalism about algorithms in society. So you can think of it as applying computers to journalism or applying journalism to computers. And by the latter, I don't mean the tech press, right? We're not going to talk about like covering new Apple hardware. We're going to talk about the effect of changes in the Facebook newsfeed algorithm on democracy, right? Which is kind of a different story. Yeah.
The first definition seems to presuppose that, that computational stories come from things that are detected computationally.
Yeah, I mean, where stories come from is kind of an interesting question. But I am presupposing that there is some data somewhere that we have to look at. I don't think you can do the sort of first direction of computational journalism without data somewhere. Data can mean a lot of things, of course, right? And you can, I don't mean you can download a CSV, right? You can make a data set. You can, and people have done stuff like this. Well, we'll look at a piece. The Guardian went through the laws in every state about same-sex couples, right? So this is pre-gay marriage, ahead of it by a couple years. And it, visitation rights, childcare, marriage or other civil union. There's this whole list of rights that same-sex couples did or didn't have in any particular state. And so they assembled this data set by reading the laws of 50 states. Is that helpful?
Yeah, I guess my question, well, I think a common question for us students in journalism schools is like, where did stories come from?
Yeah, well...
That's often the most frustrating part of the...
Like, how do you find a story?
Right,
yeah, well, I mean...
Is it always going to, in computational journalism, is it assumed that the story is always going to come from a data source, or is that something that can happen
No,
in some
I mean...
part of the story?
In the Guardian case, the data source came after the concept for the story, right? So, I mean, I guess the short answer is that it happens all different ways. Okay, so here's kind of the structure of some of the topics. Down the middle are the major topics of this course. That's more or less a synopsis of the syllabus, the things we're gonna talk about. Each of those is a pretty big topic. And then around the edges are some of the fields that we're gonna have to talk about. So this is an extremely interdisciplinary course. That's one of the things that I like about computational journalism is it's really right in the middle between the quantitative and qualitative worlds and draws heavily from both of them. And it's also very practice-oriented, right? You have to actually produce a story and publish it. So this isn't, although we will talk about some very abstract and mathematical things, this is not an abstract game. So it's really a fun place to work, and you can use it as sort of a jumping off point into all kinds of incredibly interesting areas of inquiry. And so we're gonna be talking about all of these things. We're going to start on this course with some information retrieval and natural language processing. By the end of this class, you will know how to build, Google version 1.0, right? We're going to talk about basic search engine algorithms, basic information retrieval stuff. Just in terms of the structure of the class, just to get a sense of this, okay, so how many of you are not dual degree students? Okay, yeah. So, so for you, this is a 3-point class, and for the dual degrees, it's a 6-point class. How we manage that is, if you are not a dual degree student, you don't have to do the final project. There was some confusion over that last year, so I'll remind you guys that. The rest of you, there will be a final project. We're going to start talking about it early. We're going to talk about it a bunch next class. This will be either a reported project or basically a piece of computational journalism research. it's a pretty, substantial piece of work. There'll be a sort of midterm presentation where you talk about the progress that you've made. And there'll be the last class you'll present your projects as well. So, every year there's way more stuff that I'm interested in that I get to report on personally, and so part of what I do is put a list of things on the board that I wish I had time to study, and you're free to pick any of those things or anything else, and hopefully we're going to produce some novel, either investigative journalism or research. And then there's assignments and participation. So the class participation mark, it's pretty minimal what I expect. I expect two things: show up and say something in each class, like anything. I don't care if you say like 2 words. I just want to know that you said something in each class. That's it. You get 20% just for showing up and opening your mouth. So, awesome. Yeah. There you go. You're already done. About half of the assignments will require programming in Python. However, even for the assignments that are which require programming in Python, I'm not really going to be looking at your code. I mean, I might check that it seems reasonable, but this is not a programming course. The assignments are going to have the form, write some code, explain to me what's going on. And if you can't explain to me what's going on, then you're going to have difficulty with the assignment. This is a journalism course, so the explaining what's going on is the key skill, right? It's not just about impressing me, it's about showing me that you can write about complicated topics, because that's the point. The class is pass-fail for all of you in journalism. You'll get a letter grade if you need one. The assignments are pass-fail. Every year, a few people fail an assignment. If you're one of those people, it's okay. You're not going to fail the course if you fail an assignment. It's my way of telling you that what I expect is something very different. It means, come to my office hour, let's have a conversation. You can resubmit the assignment. That's what it means, okay? So don't freak out if you're one of those people. It's normal.
When is your office?
What's that?
Are you getting that? When is your office hour?
Oh. Well, good question. We'll get to that. Probably Thursday afternoon. But we'll have to talk about when you can all attend with the other classes. Okay, so this is what we're actually going to try to cover in this class. We're going to, today. So we're going to start with this sort of very abstract concept of high-dimensional data, which, foundational to all data science, basically. And then we're going to build up the document vector space model, in particular TF-IDF vectors, and use it to talk about a piece of document mining software that is used in journalism. So we're going to talk in some detail about the evolution of that platform and how it works. So high-dimensional data. There's this quote that is something like, measurement is the most neglected area of statistics. The process of how data is produced is fundamental to all statistical work. If you open a statistics textbook, it says almost nothing about it normally. Does anybody know what this orange thing is? Occasionally I get someone in the class who recognizes it. It's actually from a children's story called The Lost Thing. And it's a very sweet little story about a boy who finds this creature on the beach and sort of adopts it. And it's not really clear what it is, and it's not really machine, and it's not really animal, and he doesn't know what it eats, and it doesn't really fit in anywhere, and he hides it in his garage. And it's a parable for not fitting in. But what I'm saying here is that the entire world doesn't fit into data. Right? There's always that arrow. That arrow is the quantification operation. There's always some crazy abstraction that happens in the quantification process. How many of you have done any sort of experimental field work? Have I ever like asked somebody survey questions? No? Okay, a little bit. Anybody done any ethnography? Okay. Anybody been involved in data entry? Census collection? Okay. We'll talk about this a lot more in classes 2 and 3, I think. But the question of data sources and data quality is this really big one that is really important in journalism and perhaps talked about more in journalism than almost anything else. As I said, statistics textbooks neglect this almost entirely. But anyway, if we can manage to convince ourselves that there's a quantification procedure, what we get is we turn real-world objects into a vector of normally numeric entries. Right? In fact, always numeric. We end up recoding categorical variables. I wonder if this will advance the slide. Nope. So we're going to work through a little example here, which is data from the UK Parliament in 2012, and there's actually a reason why I picked 2012. It's not just that that's when I built this example. This is what it looks like. Basically, we have a list of bills. You can see the titles there, and there's repeated titles because there's often multiple votes on the same bill. And a list of MPs and their votes. -9 means didn't attend, but I think 4 is no and 2 is yes. Oh yeah, it says at the bottom. Yeah. And what we have in this set of data is over 1,000 MPs and 1,600 odd votes. So the analytical question is there structure in this data? Does anybody have a suggestion on how to proceed to try to make sense of what's going on here?
What do you mean exactly? Looks like each one of the MPIDs is a vote.
Yeah, so each of those columns, MPID, is a particular person, and there's actually another table that gives their name and their party.
Party might be a good idea.
Party may be a good idea?
Just to see how which side votes on what.
Uh-huh. Yeah, so imagine your editor comes to you and says, tell me about voting patterns in the House of Lords. Right. We're looking for sort of initial exploratory steps here. Have you done exploratory data analysis in a course? Yeah. Okay, so let's talk about high-dimensional data. If this had only a few dimensions, you could just start making charts, right? And you can you can build a table that says, for any given bill, how many labor, how many conservative, and so forth voted on that bill, right? So you can sort of imagine taking sections of this, but I'm feeling ambitious and I want all of this. So we're going to talk about reducing the dimension of this space. So this space is, if we consider each MP to be an object, so we now have 1,000 MPs, so sort of 1,000 rows of data, and 1,630 votes, so now we have 1,000 data points, each of which is 1,630 dimensional. I want to visualize all of them. So the basic problem we have is we have to go from 1,630 dimensions to 2, or perhaps 3. This is a very common problem in data science. This is called dimensionality reduction, and how many of you have seen some version of this in your other classes? Okay, yeah. What dimensionality reduction techniques did you see?
PCA, TSNE.
Yeah, so that's where we're going with this. We're gonna build up the PCA today. How many of you know what principal components analysis is? Okay, yeah. So this is basically how this entire class is going to go. Is I'm going to talk about something, and like some of you will know what it is, and some of you won't. So whether you know it or don't know it, don't feel bad. The basic technique that we're going to talk about is projections, right? So what projection is it is a classic, in fact, ancient technique for dropping dimensions. Although this form of it was actually worked out during the Renaissance. And some of you may be familiar with techniques where painters would look through a sheet of glass or rig strings between the points of an object and the central eye point and plot their intersections. The mathematics of this were worked out 400 or 500 years ago. And you can think of it as finding a direction to look from and then dropping the depth dimension. So this finding a direction to look from is pretty important. And I'm going to go to my favorite rotating cube. So this is a data set. This might be the iris data set, where there's a bunch of points. And in this case, the points are in 3 dimensions. And we're looking at a 2-dimensional picture, of course. And we're trying different angles on this. And what I want you to notice is that in some angles, the clusters really overlap. So, the red and the black will be on top of each other in a minute. And if you're trying to see clearly there you go, right? So if you weren't already coloring them red and black, you wouldn't really be able to see what's going on there. And so, for example, this is not a particularly good direction to look from because everything's overlapping. But there are other directions where you get a lot of separation between the points. And those are directions you want to look in. And the theory of PCA kind of goes like this. So let's do sort of the simplest possible example where we're projecting from 1 dimension, or from 2 dimensions to 1 dimension. And is there an eraser over there? If you could hand me the other markers too, that would be lovely. Oh wow, look at that, so many. Okay, so we've got these data points. And let's say they're in 2 big groups. And we've got these 2 axes, which we're going to call x1 and x2 because that's sort of convention in data science. X is the coordinate or the input. And we're going to project them down to 1 dimension. Now, we can project from any direction, but let's just limit our choices here and say, do we want to drop the x1 or the x2 dimension? Well, if we drop the x1 dimension, then what we're going to get is the positions of these things projected onto this axis. And I'm not going to draw this little projection for everything here. But you can see that they're really going to pile up on top of each other here. If we drop the x2 axis instead, we're going to get some pile up. That's what happens when you drop dimensions. But we're also going to still be able to make out that there's 2 clusters. So we've preserved a little more structure. Now, the question is, how do we automatically pick which axis is better to project? Right? Which axis is better to keep, basically? Any ideas?
You want like a distance function, and you want the distances in the R2 dimension between points to be as preserved as possible in the R1.
I think you are building up the intuition behind the MBS algorithm, which we will also get to. But yes, good. A simpler answer.
Less piled up.
What's that?
Less piled up.
Less piled up, yeah. How do we know how piled up these things are?
Distance.
What's that?
Distance.
Distance, yeah. Something distance. So a simple heuristic to try to pick a good projection direction is just look at the overall range of the data and preserve whichever dimension has more range. Right? They're going to be less piled up. It may not be ideal, but it's going to get a lot of it. And in fact, instead of minimum and maximum, what we normally compute is variance, which is the standard deviation squared, as you'll recall. And so the entire notion of PCA is that we pick the first dimension in PCA is the one which has the highest variance. The second one is the direction which has the second highest variance. And all of them are perpendicular. So what we ended up with is a set of perpendicular directions which have the first, second, and third highest variance, and so forth. So when you put that into math speak, you end up with eigenvectors and covariance matrices. How many of you have done the whole eigen thing? Any of you have that background? Yeah, some of you will have been forced to do this. So typically you'll do this in like second or third year linear algebra, right? And it's one of these things where you just sort of go, why am I learning this? And it turns out the answer is because it's actually an incredibly foundational concept. But not really for us, because we don't have to compute it. We're going to do this in one line of Python code. But this is what's happening, right? We build this covariance matrix, and the covariance matrix is the diagonals of it are the variance along each direction, and the off diagonals are the variance between two different coordinates, and that matrix actually encodes all of the information about whatever way this thing is rotated in space. And then we just sort of pick the however many directions we want. So for directing to 2 or 3 dimensions, we pick the top 2 or 3 eigenvectors, which end up being the directions of maximum variance. So we're going to run this on the House of Lords data in a second. Before that, I want to talk about why. And basically, we want to find structures in the data. And the simplest structure that we can find is a cluster. And the reason that clusters are interesting is they produce a sort of natural classification of the data. Right? So think about going out into an unexplored country, perhaps as Darwin did, and or at least unexplored by Western naturalists, and cataloging all of the species that you find. And so you walk around, and you have no idea what's there, and you say, okay, so there's a small creature, and it has 4 legs, and it's green, and it's amphibian. And there's another creature, and it's in a tree, and it has feathers, and it's brown. And here's another one which is green and amphibian. And here's another one which is also green and amphibian, but it's smaller. And you end up, sort of plotting these characteristics, and eventually you're like, okay, well, I've got some brown birds, some frogs, and some green grasshoppers, right? You've deduced the categories from the structure of the data that you observe. And so that's what's happening when we're doing clustering. And this is super important. Categories are foundational to language and thought and basically all analysis. And so this is why clustering and categorization is such a fundamental thing to do with data. And we're gonna see this in a bunch of different contexts. Clusters are perhaps the simplest important structure that you get in data. And this is a whole book on classification systems, which is awesome. And there's another book called Sorting Things Out, which is about how our classification systems affect our, not just our thought and our language, but actually our institutions and our processes. Like, think about whether something is classified as a mental illness or not. Right? That can have huge effects on an individual's life course. And that's just a classification change. So we're going to do this. So I'm going to show you what this notebook looks like when we actually do it. And you can follow along. Did I post the online version of this? Let's see. Oh no, I made a repo just for this. A new repo, which I will post to Slack. No, that's the old repo. Here we go. So here's the idea. So we read these votes, and I reduced it to just the last 100 votes. So this data is a little smaller. It's 100 votes by 613 MPs. And this is a bit different from the one we saw on the slide. This is just to make this exposition a bit more straightforward. So here's the ID, which you can key back into the original data if you want. Here's the party, conservative. XB means crossbencher. We're now sort of getting into the details of British politics. Labour, Liberal Democrats, Labour. And I've recoded them so 1 is yes and 0 is abstain, and -1 is no. So there it is. Then I'm going to write this little function which color codes them. So this is kind of our legend. And we get black if we don't know it. And then this is the actual, we're starting to actually view the data. And if we don't have dimensionality reduction, we kind of have a problem because we can view 3 dimensions at a time. So each of these dimensions is a vote, right? So this axis would be the vote on vote 22, I guess. And we've got a bunch of problems here. So first of all, what is this pattern we're seeing? Why do they have this shape in the scatter plot?
Because there are two groups, like -1, 0,
Yeah.
1, 0.
Yeah, basically we're getting all combinations of -1, 0, and +1 on these 3 axes. So these things are also piling up, right? There's actually like 100 dots piled up here because we've got 613 total. You can see some combinations don't exist, but basically we have 3 times 3 times 3, 27 dots. So it's not really telling us anything about the voting patterns. And so what's actually going on here is that this is the intuition I want you to develop. The eraser go. Oh, yes, okay. This is the intuition I want you to develop. We are looking from the wrong direction, okay? So you can talk about TCA in terms of like eigenvectors, and like you can do this all symbolically with a lot of linear algebra, but it's really all geometry. And if you can get comfortable in high-dimensional geometry, then you can talk about all of this stuff in geometric analogies. And this is what's going on. So if I project to this axis or this axis, what I get are 3 blobs, right? If I project to a diagonal axis, I get something more interesting. I get five blobs, the center of which are a little heavier, because there's more dots that are stacked up here. Okay? And so, if in fact what happens is that most of the MPs voted here, for example, so this is actually like 10 dots on top of each other, then I'm going to start to see that when I look from this direction, because I'm going to start to see these piled up. As you add dimensions, this diagonal view, which you can think of as just taking a sum of a bunch of different votes simultaneously, a bunch of different dimensions simultaneously, start to be more interesting, because you're looking at, here you're looking at the sum of 2 votes. If you go into 3 or 4 or 10 dimensions, you're starting to look at the sum of 10 votes, and then you're starting to see more values than just the 3, -1, 0, +1. So what we're going to do is we're going to let the PCA algorithm pick the dimension. And I told you it was easy. Here it is. So this is what we get when we reduce it to 2 dimensions. I've done one other thing here, which is I've set the colors to the party. So, first of all, you can see a lot more structure. If you look at the colors, so Liberal Democrat is yellow, Labor is blue, Conservative is red. So as you would expect, Conservative is red, Labor is blue. So we've got sort of left and right here, which tells us something a little bit about this political axis. And then we've got this other axis, which is, remember, the axis with the second most variation, which is where the yellow, right? So the Liberal Democrats, which is where they are. Now this plot actually corresponds to the political structure of the government at that time. Does anybody know anything about the UK government at that time? Yeah, when I taught this course in previous years, people were like, yeah, this is happening right now. No one's ever going to get this question again, so I'll just show you. They had a coalition government, which is something that only happens in parliamentary systems, where they eventually had a coalition between the Conservatives and the Liberal Democrats. So what you are looking at in this example is the red and the yellow are in a coalition government together, but they're not really voting together. But the Liberal Democrats, who maybe you think would vote more often with Labor, the blue, end up sort of voting distinctly differently from the blue party, but not quite the same as the red party as well.
What are the axes?
Right, so that's the question, right? What are the axes? What are the axes? What's that?
One of it's like how the range of vote on each of the different issues, like the bills, like which side of the bill that they vote on, and then the other being like the political leaning.
Yeah, kind of. I mean, so here's the thing. The actual answer to what are the axes is the axes are the dimension. The first axis, the horizontal axis in this picture, is the dimension along which there is the greatest variance in votes. The y-axis is the dimension along which there is the perpendicular dimension along which there is the second greatest variance in votes. So from a technical perspective, that is the answer. But I think really what the question that you come up with when you look at this picture is, okay, but what do the axes mean? And to figure out what they mean, the only thing we can do is go back to the data. And so just looking at this picture, which is only interpretable because we put colors on the dots, right? If this was a black and white picture, you'd be like, okay, it's a T shape. But knowing that conveniently conservatives on the left and laborers on the right, you can see that the first dimension is something like the left-right political axis. And actually in every voting pattern analysis and social attitude analysis that I've ever done or ever found in the literature, the left-right axis just pops out. For a while, I had this question, is the left-right political divide real? Right? Is this thing that people talk about, do people actually split that way? Or is this just sort of a narrative that we impose on the world? And it turns out it's real. It's real. It tends to be, for some reason, the first axis of variation in political attitudes seems to be this left-right axis in a pretty traditional sense. Now, exactly what left and right means will vary in each country, but you always find it. What does the second axis mean? So this is clearly the direction in which the Liberal Democrats vote, which is some other policy dimension. To figure out what that dimension is, what we would have to do is we would have to look at what bills are assigned to that dimension. So what do I mean by that? I'm also talking about what is called the loading on the components. And what you actually get is, I don't remember how to do this now. Scikit PCA loadings. Also known as factor loadings. PCA components. Okay, so here we go. Where to go? Okay. And we called it model. All right. Oh my God. Numbers. Okay, well, let's see what shape this is. 2, 100. So notice I had 100 votes here. Right, I had 102 columns because I also had these two, but I just used the voting data. So this has as many columns as votes, and then it has 2 because I asked it to build me a 2-dimensional projection. And so what I end up with is 2 100 vectors. And so what that is a coefficient for each bill. And think of it this way. The PCA algorithm takes some dimension to project, right? And so, if it was just the horizontal dimension, then my vector would have 0 everywhere and 1 in one place. Or same with the vertical dimension. If it was really this diagonal direction, we're all exactly like a 45 degree, then it would have the same value in every component. But instead I'm going to have some direction which is like this, right? So it's not exactly diagonal, but it's not actually horizontal. And it's a direction, right? It's a vector. And the components tell me the direction of that vector. So now jump up a dimension and imagine this in 3-dimension. It's a plane. And in higher dimensions, it's actually a hyperplane. And as you all know, a hyperplane is represented by a vector, which is actually the normal vector of the plane, right? So these numbers, the coefficients here, which let's look at the first one, for example. Right? This is actually each of those numbers tells you how much weight you put on each bill. So if you go and you look at this and you take the directions which have the largest value, right? So a lot of these are really small, like 0.03 or something, but a few of them are bigger, like 0.19. That tells you that those bills are counted most heavily in that direction. So that's like the leftist or rightist most bill. And, but I looked at component 1, which is the vertical one, right? So that bill is really characteristic of this direction. And so all of these yellow dots tended to vote yes on that bill. So we could go through these coefficients and go back and read the titles and text of the bill and figure out what it means to be more vertical. And what we're going to find is we're going to find all the bills where the Liberal Democrats voted yes. Right? Which we can already tell that because that's what that shape means. Okay? Questions?
When you say like the direction of the second most variance,
Mm-hmm.
is that like, do you like recompute the variance once you've done the first projection?
Yeah, kind of, right? So like I said, I gave you this nonsense earlier, right? First k eigenvectors of the covariance matrix, corresponding to the largest eigenvalues, right? So one algorithm for doing that is you find the direction that has the largest variance. Never mind how, you just find it, that's the largest eigenvector. And then you're like, okay, now let's find the direction which is perpendicular to that, which has the largest variance. And you just keep adding perpendicular vectors, adding as much variance, whichever direction has the most variance each time. So that's how it's actually computed. But once you compute it, it's done, right? Because the data is static.
Fair.
Yeah.
Going back to the Jupiter notebook, you said that the Labour Party had a coalition government with the Conservatives, right?
Yeah.
So why is it that it seems like, at least in this PCA version, it looks like the Labour Party is like, if you project along the x-axis, closer to the Democrats, the Labour Party?
Because we have intentionally tried to find the direction in which they're as different as possible from everything else.
Yeah.
That's what it means to have the direction of the second most variance. So it's going to find the direction that they go. A little bit later, we're going to look at a multidimensional scaling plot of this, where we plot things based on distance, and you'll see that actually they overlap.
Okay.
So it's a different view of the data. Yeah.
How do you go about explaining this? If you had done this and you want to maybe publish like this visualization or something, how would you say this would work?
Yeah, great question. So I would say that, each MP is given 2 scores, each of which is a weighted average of their votes on a certain set on the bills. One set of weights is includes bills that vary along the traditional left-right axis, and the other set is just those bills where Liberal Democrats tend to vote differently. So that's sort of one way to think about it. I think that's probably still too much because most people are not familiar with weighted averages. I think the first order version of this gets to be something like they're plotted on 2 axes. The first axis, the horizontal axis, represents the major left-right divide. The second axis is the ways in which Liberal Democrats differ from the other parties. It gets really metaphorical. So this is a key theme in this course. You'll remember this from the lead course. Is the mapping between the words and the data, other words than mathematics. And this is one of the reasons this is so much fun and so hard, is because we're really straddling the quantitative and qualitative here, right? We're trying to find words that not only are an accurate description of what's going on in the data, but that people will understand, right? So we have to map not just the meanings of the words, but the meanings that will be understood when we publish this publicly to people with no technical knowledge. And I'm not necessarily recommending that you publish a PCA plot, but I'm not saying that you shouldn't, but it is a little hard to describe. But I want all of you to know how to interpret these, because it is perhaps the simplest way to visualize the basic structure of a high-dimensional data set. All right, thoughts on that? Okay, so that's PCA. Oh, did I have this in 2 places? Oh yeah, okay. Slide issues. There is another approach, another fundamental approach to understanding the structure of high-dimensional data, which uses distance metrics. And a lot of things uses distance metrics. And for example, all of the filtering algorithm designs that we're going to look at in the next class are built out of distance metrics. So let's talk about them. Formally, a distance metric is a function with these properties. So they have names like reflexivity and so forth. These are meant to model our intuitions about geometric distance, right? So if I'm looking at the distance between 2 points, it's not negative. The distance of anything to itself is 0. Distance from green to blue is the same as the distance from blue to green. All of those are obvious. The triangle inequality is, I think, a little less obvious. You're all familiar with the triangle inequality in geometry. It's another way of saying that the shortest path between 2 points is a straight line. It says if you go from, what are we talking about? If you go from x to y to z, it can't be shorter than going from x to z directly. Okay? So these actually impose a fairly strict set of constraints on the topology of the underlying space. But there's a bunch of stuff that does this. So normal Euclidean distance will satisfy this, but so will things like distance on a graph. Right? So if I have a set of nodes, and I have some edges, and the edges are weighted, with some distance on them. That's 10, that's 3, and so forth. Then if I define the distance metric between 2 points as the sum of the weights on the edges of the shortest path, then this will satisfy this. Okay? So it actually applies to a lot of different situations, more than you might think. And if we have a distance metric, then the space that the objects are in, so these x and y, they live in some abstract geometrical space, is called a metric space. If we have a distance metric and we have n points, we can make a distance matrix. Now, this is distinguished from the data matrix. So we saw the data matrix for the House of Lords. So this is the data matrix, right? We have one row for each object. So that can be of whatever size, right? M objects of n dimensions. The distance matrix is always square, and it's always symmetric. Why is it symmetric? Yeah, because we said that it's symmetric, right? So it is a symmetric matrix with of m times m, m objects. And we can always compute this thing if we have a distance metric. It's going to be big, right? This starts getting scary if we have 1,000 points. Now we've got 1,000,000 entries in the matrix. And if we have 1 million points, well, so sometimes you don't want to compute this explicitly, right? Sometimes you want to do it on demand, or you want to make it sparse or something. But in principle, we can just store this thing in a variable. And we can use the distance matrix to create visualizations of the space of objects, which Vivian, you were getting at earlier with the sort of distance preserving embeddings. So let's talk about that algorithm. This algorithm is called, we're talking about clustering. Yes, before we talk about creating visualizations, we're going to talk about clustering algorithms. There's tons and tons of them. This is sort of like pretty standard data science stuff. But if you think about them, you'll notice that they all require a distance metric. So the fundamental thing you need to do clustering is how similar are two things, right? So I'm out in the field, I'm exploring my new country, and I notice one four-legged green amphibian and another four-legged green amphibian. Are they similar enough that I'm going to say the same species, right? Or is one a frog and the other a salamander? So presumably my distance function will tell me that any two frogs are have a lower distance to each other than any frog and any salamander. Okay, that's the idea here. And if that is the case, then we can find mathematical structure here. How many of you have seen the k-means algorithm? Yeah, right, okay. So we'll do that pretty fast. This is a really classic algorithm. So, restart. All right, so you pick. How are we going to pick the initial centroid? So in other words, we're trying to find the center of clusters. To do that, we need an initial guess for where the cluster centers are. Randomly, okay. And then what kind of data would you like? Smiley or pimpled smiley? Pimpled smiley. Pimpled smiley is really the best one. Okay, so here we go. The way the k-mean algorithms work is, so the big limitation of k-means is you have to pick k before you start. You have to know the number of clusters before you begin. And there are clustering algorithms which don't require you to know that, but k-means does. So there's a centroid. What should we set k to? How many clusters do we think we have here? 4, okay. So there's 4 random centroids, and what it's done is it has colored the regions of space which are closest to each centroid. So, for example, the border between the red and the blue is going to be on a line which is equidistant from each, right? That's what defines these lines. So now, the k-means algorithm has 2 steps. The first step is we figure out for each point what's the closest centroid. So there you go, we've colored them. And the next step is we move the centroid to the centroid of all of the points that have that color. So you all know what a centroid is? Centroid's a fancy word for average. It's a geometric concept of an average. So there we go. And then we repeat. We've changed what points are closest to what. And you can see that, for example, we've got some red points in the blue region, right? So we reassign all of the points. And then we move the centroids again. And we keep doing this. And eventually what happens is we reach a step where we don't assign any points. So I think we're going to reassign just a few here. And you can see that sometimes it takes a while to converge, but you can actually prove that this will converge. And eventually it stops. There you go. We've reached convergence. Okay. So there's a proof that the k-means algorithm will converge. It's not necessarily going to converge fast, but in practice it does pretty well. You can get away with 10 iterations or something. What do you think? Are these reasonable clusters? Have the centroids captured the structure of the data? Yeah, it's kind of a hard thing to add clusters. This makes more sense when you do something like, well, okay, right? Like, it better find these. So let's try it. Right, okay. Right? So obviously, clustering only really makes sense if the data really is clustered. Real data is kind of somewhere in the middle. We'll look at some real data in a bit, clusters of documents, and you'll see that it's, there's cluster structure, but it's pretty messy. So this is the k-means algorithm, right? And when you look at this, I want you to imagine doing this in some high number of dimensions. We're doing it in 2 here, but it certainly works in 3, and in fact, it works in any number of dimensions, and all of the proofs go through. And in fact, if you build a clustering algorithm, so think about what you need to build the k-means algorithm to implement this, right? So the first step is you would assign each point to the closest centroid. Well, the centroid is a point, and the closest, well, what does closest mean? Well, that means least distance. So if you have a distance function, then you can do that step. And that distance function could be in any number of dimensions. And then the only other thing you need is you need to be able to create a centroid. So you need to be able to take a bunch of points and average them somehow. So if you have an averaging step and you have a distance function, you can implement k-means. And there are other clustering algorithms which only use a distance function. So if you know how to take a distance function between 2 points in your data, and there's some pretty obvious distance functions that work in, any number of dimensions, like Euclidean distance, right? Then you can cluster in any number of dimensions. You don't have to change your clustering algorithm. So all this stuff works in high dimensions. So I'm not going to run this in the notebook, but you can run k-means or whatever clustering algorithm you like. I think I used a hierarchical clustering algorithm here. And I said, tell me which cluster each MP is in, and this is what you get. Ta-da! Now you get a number for each MP. The reason that I've showed you this is because I want to point out, and I will point this out over and over again, is that data by itself never has meaning. The meaning comes from connecting the data to the world in some way, right? And if you don't believe me, I'm going to take some of my favorite spreadsheets, remove all the column headers, and send them to you, right? And this is, again, one of those neglected topics in statistics. It's like, well, the data only has meaning when it's connected to everything else. So we're going to connect it to something. In this case, we're going to connect it to party. So now I've added at the top there is the party of each MP. So you see the party, and then immediately below it, the cluster. And if you stare at this for a bit, obviously there's better ways of visualizing this. But if you stare at this for a bit, you might be able to convince yourself that it's picked up party information. So Labor is usually 2. Liberal Democrats are normally 1. Crossbenchers are normally a thing. But take a look at the Conservatives. They're usually 1 as well. So it's ended up putting the Conservatives and the Liberal Democrats, who are in a coalition, in the same cluster. And that is because what I did when I did this is I built a distance function that computes distance based on the number of votes in common. So I think I'll actually show you this. So if you look at this original post, I don't think I have the code. Yeah, here we go. This is the distance function I used. And if you stare at this for a few minutes, maybe you can convince yourself that this follows the rules of the distance function. So, for example, it's symmetric in V1 and V2. You can switch them and you get exactly the same thing, right? Because everywhere they appear, you can switch them. If they're the same thing, right? If I pass the same MP for both of them, this is going to give me 0. Triangle inequality is a little harder to prove, but you should be able to convince yourself that it works out. And all it does is it basically counts the fraction of both where they both voted and they both voted the same, right? So I figure out how many bills they both voted on, because not everybody votes on everything. And then I figure out, well, how many do they match on within the ones where they were both there? And then I figure out this fraction, the number where they match on divided by the number where they could have matched. And I take a 1 minus because this will be 1 if they voted identically. But it needs to be 0 if they vote identically, so I go 1 minus. Okay? So that's the distance function I designed to do this. And we're going to turn this into a visualization in a minute. Oh yeah, so there you go, it says at the top. This may seem a little arbitrary to you, and it is. So here's the thing about distance functions and clusterings. They're not objective. And subjective isn't a bad word. Subjective, one of the ways to think of subjective is set by contextual considerations. So, for example, I am using domain knowledge of how Parliament works and what voting is to decide that this is a useful distance function. Now, I'm still making a choice. I'm saying, well, let's look at how well they agreed where they both voted, rather than looking at, you could also say, well, let's just look at the number of votes that match, and if one person was there and the other person wasn't, then let's just say it's a mismatch, right? So we still have a bunch of choice here. And there isn't going to be a right clustering or a right set of categories. There are only going to be a useful set of categories for your problem. This is my favorite example. At the top, we have this is due to Clay Shirky. At the top, we have the piece of the classification system for the Soviet National Library. And at the bottom, we have a piece of the Dewey Decimal System. And you can pretty clearly see the philosophical influences of each of these categorization systems, right? They're both categorizing the same thing. They're both categorizing books, but they have really different ideas of what a category is. I love that 290 is every non-Christian religion. Right? So this was invented by Dewey in the 19th century. And so, like, you know, in the libraries, in American libraries at the time, this was a reasonable way to do it. In fact, there is a justification for this, which is that, anybody know the difference between a typology and a taxonomy? So these words were used in the title of this book. What's the difference between a typology and a taxonomy? Anybody know? A typology is just a series of types. What types of things can we have? So your typology would probably have books of all kinds of different religions. A taxonomy is a typology built up from the objects you actually have. And so this is why the Dewey Decimal System is so Christian. It's because at the time it was made, that was the set of books in the library, right? It's a completely reasonable thing to do to build up a classification system from the examples that you actually have. So going back to exploring the animals of a new country, you're building up a taxonomy. So the tree of life is a taxonomy. It is a classification system designed to be effective in categorizing the actual species that were found in the field by naturalists, as opposed to, I guess, sort of hypothetically or based on theoretical considerations. Anyway, you're going to run into these issues when you're designing distance functions and doing clustering, right? Like, there's no unique clustering. We're going to move from clustering to visualization. They're often very closely related. But remember that technically speaking, a clustering algorithm just produces cluster assignments, right? So the output of a clustering algorithm is this. In fact, it's not even that. It's that. Which is why we still want visualization, because we would probably take the output of a clustering algorithm and then visualize it. For example, by assigning colors on a plot. So just a reminder of that point. So we're going to talk about a different way of visualizing this high-dimensional space. So the PCA projection is a linear projection. That means a couple different things. Geometrically, that means what we do is we drop straight lines to a straight surface, right? So I'm going to repurpose these points as points in a Euclidean space again. And I'm going to say, well, we're going to take a flat projection plane, right? So this is some hyperplane. And then we're going to take the perpendicular distance, which is, of course, also the shortest distance of each point to that plane. And then we're going to take the points on the plane that are the closest distance, and that's our projection. Right? So that's what we mean by a linear projection in geometric terms. In linear algebra terms, what we mean is that we do a matrix multiplication. And are you all familiar with the rank of a matrix? Okay, so you can think of the rank of a matrix as how many dimensions you have left after you multiply by that matrix. And the fact that this is a projection means that that matrix has to be less than full rank. In fact, if you're projecting to the screen, that is projecting to 2 dimensions, that has to be a rank 2 matrix. It has to drop every other dimension. Now, in some basis, that matrix will have 0 for every row except the first 2. But in general, because this is on a diagonal in whatever coordinate system, the matrix is still full of numbers, but you're going to find that it projects everything to a single point. So this is what we mean by a linear projection. The projection we are going to use is a nonlinear projection. It is still a dimension-reducing function. So we still end up on a plane, but we're not doing it by dropping perpendiculars anymore. So in particular, a linear projection preserves certain types of distances and angles. So obviously a linear projection doesn't preserve all distances, but it preserves distances. It preserves this distance, right? It preserves certain types of angular relationships as well. A linear projection doesn't have to preserve anything. And there's a fisheye lens, which is a simple nonlinear projection. So here's what we're going to do. We're going to build a nonlinear projection, and instead of starting with the positions of all of the points and multiplying them by a matrix to flatten them out, what we're going to do is we're going to start with the distance matrix, right? So the distance between every pair of points. And if you think about this, if the input and the output dimensions are the same, then actually I can get all of the coordinates back if I just know the distances, right? So say this is a map of say these are the positions of a bunch of cities, and these edges are labeled with the distance between them, so as the crow flies. And I don't give you the positions of the points, but I give you all of the lengths here. Right? I just give you a list of the distances from every city to every other city. If you think about it for a second, and you can prove this mathematically if you wish, you can recover the positions of the points just from the distances, up to a scaling and translation, right? So I may not know which way this is rotated, I may not know where it is on the plane, but I know it's going to have this shape. So a distance-preserving transformation preserves, in particular, the geometric properties we're interested in. It preserves all of the relative lengths and angles if you go from 2 space to 2 space or 3 space to 3 space. But there's nothing that stops us from going from like 100 space to 2 space. We just may not be able to get all of the distances exactly, right? You can't satisfy all of the original distances in the low-dimensional space. So this is a classic algorithm. It started in 1952 called multidimensional scaling, and it's, here's some linear algebra. Really the only thing I want you to think about here is, so we start with the distance matrix on the left, and we end up with coordinates, right? So it maps distances to coordinates. And it says, well, we're not going to get exactly, right? So x are the coordinates, and b is this transformed version of the distance matrix. Basically, we sort of subtract out the means. And that line 6, this minimizes b minus xx. What that's saying there is it minimizes the disparity between the coordinates it's computed, or the distances between the coordinates it's computed, in other words, the distances in low-dimensional space, and the distances in high-dimensional space. So that's what we're doing. And there's a bunch of flavors of this. And so this minimization, see that in 6 there you have that double bar, that is a matrix norm. It's a standard squared norm, and if you sort of grind through the math and you work this out, this is what you get. That norm ends up being the squared sum of the difference between the high and low dimensional distances. So the x's here are the computed coordinates, right? So we're trying to figure out where to place these points. That's the output of the visualization. The d's are the distance matrix elements. And what we're doing is we're trying to minimize the squared difference. And how many of you have had some basic physics? Anybody know the physics of springs? So Hooke's law, anyone? Hooke's law?
As you like, there's like a squared relation somewhere between like pulling out a spring and the force.
Yeah, not right. So actually the force increases linearly, but the energy it takes to stretch a spring is proportional to the square of the displacement. And springs have a rest length, right? You can both squish them and you can pull them. And so that squared, and there's a spring constant, but the spring constant sort of drops out here. So that minimization is actually identical to connecting all of these points with springs that have rest length equal to the distance in high dimensional space, and then waiting for them to find the lowest energy configuration, which is what they'll do if you just let them sit, right? If you connect a bunch of things with springs and you let it wiggle around until it stops, you're going to find the lowest energy configuration. So there's actually a very intuitive physical interpretation, which is that you connect everything with springs and wait for it to settle down, which means actually you can calculate this, and you'll see this in a second, and I'll show you visualization when we talk about the overview system. You can calculate this just by pretending there's forces on these dots and simulating them at each time step with the dots moving according to the spring force. And so another way I think about this is that you have a bunch of these points have this sort of connectivity between them. It's this like stretchy structure, and I take this high dimensional structure and I flatten it between two planes of glass, and it squishes down and the springs pull it around and it sort of creaks and wobbles and eventually stops. And that's multidimensional scaling. So if I do this to the House of Lords data, this is what I get. This is that blog post again sort of goes into more detail. And you can do this in Python. I just haven't done it in the notebook we looked at. It looks a bit different from the PCA plot. And I think there are a bunch of reasons for that. First of all, what do you see? What is the relationship between the conservatives and the liberal Democrats in this plot? The colors are different, I apologize. Yeah.
The same part. They're on the right.
Yeah, so they overlap a lot more. So the liberal Democrats in purple don't quite overlap the conservatives in red, right? They tend to stretch a little bit towards the left, towards the labor in this case. But they're definitely in the same quadrant, right? And then the other fun thing here is the green dots, XB, those are the crossbenchers. Those are MPs who will sit with either party. That's why they're called crossbenchers. And sure enough, they vote all over that place. So this gives a very different picture based on the distance in between voting patterns. And what might be going on here. So first of all, I think the major differences are just the fact that rather than trying to find the direction where the liberal Democrats are most different, right, the second most variance direction, we're just trying to put everything down and be distance preserving. So you can see there's clearly an axis where the liberal Democrats differ, right? They sort of go out this way, but that axis has been flattened down by this projection. So that's one thing that's going on. The other thing that's going on is it could be that the liberal Democrats just vote on a completely different set of bills than everyone else. And we don't see that in the PCA plot because we take every bill, whereas our distance function looks at only bills where both people voted. Right? So we've actually got a difference in what we're doing. And in fact, in the blog post, so here's that one we were just looking at. If we change the distance function, right, so I modified it rather than just the number of votes where they overlap, I'm modifying it by this factor, which is, okay, but how big is the overlap, right? So, and I'm taking a log here just to try to squish the scale a bit. You can start to see sort of how I suppose it's technically correct to say subjective. I think, prefer the word contextual here, right? There may be strongly justifiable choices for why you do these things. In this case, because I don't get an interpretable plot if I don't do this log thing, right? I'm adding this other factor, which is, okay, well, let's push two MPs apart if they didn't vote on the same bills. So if the overlap is 0, well, I guess I don't run this line at all, right? So if the overlap is small, then this will be very close to 1, so we'll get much bigger distance. And when I do that, this is the pattern that I get. I get a different shape, and you can see that the liberal Democrats now start to push off up here, right? So I think this axis, this vertical axis, is kind of like the people who don't share a lot of votes with anyone else, they sort of end up there. So I think that's part of what's going on, although you can see that conservatives end up there too. So anyway, different projection methods will emphasize or allow you to see different aspects of the structure of this data. And again, asking which one is the right method is kind of like asking what is the right method to analyze data. It's like, well, depends on the question you're asking, right? There isn't going to be a single answer to this question. Okay. Yeah, and here I'm sort of saying the same thing, right? So there's all of these free variables. There's all of these places where our domain knowledge, our knowledge of the actual real-world problem comes in. So maybe we shouldn't even be looking at votes if our question is about how people are working together. Maybe we should be looking at committees. Maybe we should get the transcripts and do text analysis. I don't know. Maybe we should look at voter behavior and not legislature behavior if we want to talk about polarization. And then also we have to ask, okay, but what is the rhetorical structure of the argument that we are going to be making? Right? What are we saying? And different data analysis methods will support us saying different types of things. So this is our first mention of robustness in this course, is the word you're going to hear me say a lot. If different analysis methods give you different stories, you have a problem. Right? Well, it's not necessarily a problem. It's a problem we know how to deal with in journalism. If different sources give you different stories, you have to reconcile that in some way, right? You have to, either somebody's giving you inaccurate or incomplete information, or opinions really do vary, and you have to represent that in your story. So it's the same thing with data analysis. What you're hoping for is that different methods, a variety of different methods, including non-data methods, right? Including qualitative methods, will give you qualitatively the same answer, and then you have a very strong story. It's like if every source is telling you the same thing. Okay, so our next topic today is text analysis. And I'm going to start by just showing you some examples of what people have done with it, and then we're going to develop the TF-IDF model, and then we're going to show the development of this text mining system, which I think, given the time, we will probably have to do next class. Text analysis could mean all types of things. Here's a story I worked on for ProPublica. It was about a child foster care facility in California called Level 14, which, anyway, long story. It had all sorts of problems. But what I had to do was extract incident type from a bunch of documents that looked like this. Right? So these were scans, redacted scans that we got that OCR'd with a lot of errors, and I had to basically get date and type. So it's basically just a big data extraction problem, and this is very common. Analyzing a document set could mean a lot of things. This was from a story that came out of Reuters on basically these Yahoo News groups where people were, how to put it, let's call it unauthorized adoption, right? They're trading children. And they went through, it was a public news group, there were private news groups as well, but to avoid sort of various types of legal complications, they went through a public news group. They went through over 5,000 messages, and they had to determine by hand that each certain messages were talking about particular children. And then they broke down the demographics in a bunch of ways. So this is basically a counting analysis, but it's a very complex counting analysis. Analyzing Twitter data is still enormously popular. Twitter is the E. coli of social network analysis, right? It's the model organism. It's all public, so it's really easy to get the data. Everybody knows how to use it, right? So everything's done on Twitter, even when it probably shouldn't be. This is just this piece that looked at the demographic breakdown of who talked about particular hashtags. And then sentiment analysis. It doesn't really matter what I say. All of my students want to do sentiment analysis on Twitter. I recommend against it. It's a very appealing notion, right? The idea that you can track how the general public feels about a topic. You can't really do it, though, for a couple of reasons. One is that sentiment analysis is more complicated than it seems. Even humans only get about 80 or 85% accuracy on sentiment analysis because language is pretty ambiguous. Sometimes you can't tell how somebody feels from a 10-word tweet. The other problem is that Twitter is just not even remotely a random sample. I mean, leaving aside the question of the demographics of the people who are on Twitter, I mean, tweeting about a topic is intense self-selection. So without really sophisticated modeling of who talks about a topic at all, it's very hard to understand anything. Nonetheless, there was a sort of peak in, I think it sort of passed about 4 years ago, of people doing Twitter sentiment analysis. In my mind, this is a much better use of sentiment analysis. So rather than trying to ask how people feel about an issue, what they did is they looked at how draft versions of Inspector General reports differed from the published versions. And the way they did that is they used sentiment analysis to find cases where the language was softened. And there's a nice recording from an ICAR conference a few years ago talking about this. I also talk about this case in a paper, which we'll look at a little bit later. And one of the interesting things about that is they had to retrain the sentiment model to work on these reports. This is very common with sentiment analysis. It's also one of the problems is everybody's like, I know, I'll use LTK. But generally, sentiment analysis is very domain dependent. So in this domain, for example, the word recommendation, which is normally a positive word, these are audit reports. So recommendation is a negative word, right? If you have a recommendation in an audit report, it means they found something bad. So it's kind of interesting. I think 400 negative references were removed, right? So they didn't want to count all those manually, so they built a sentiment analyzer that would work for this domain. Classification is one of the most common types of text analysis. We saw a very sort of complex manual version of that in the child exchange story. This is a much simpler classification problem. All you want to know is whether, starting with a description that the police recorded about a particular incident, was it an aggravated assault or a regular assault? And I've never forgotten the definition of aggravated assault. I think that's where you touch the person. Anyway, so there's a criteria for whether something counts as one or the other. And you can read the incident report and decide. And what they found by piloting for the year of this, by going through a year of data, so about 20,000 reports, is that many assaults were misclassified as less serious than they were. And then, starting from so they went through a year of this stuff, and that generated training data, and they used the training data to train a classifier to train all of the rest of it. And we'll look at this in more detail. But document classification is a pretty standard technique, and it's been used in a bunch of journalism. Oh, and here's what it looks like. So I love the language that they use here. Like, BICs and susps became in a verba arguments. Anyway, it's, I keep talking about domain knowledge. This is what I mean. Standard algorithms will not work for journalism. The algorithms you learn in textbooks, or you load from scikit and NLTK, or you're going to learn in class, generally won't work. They can often be made to work, but out of the box, they're not going to work for a variety of reasons. We're also going to look at topic modeling. How many of you have encountered this, like LDA-style topic models? Okay, we're actually going to get into those next class, and you'll have an assignment on them. This is a popular method to, well, you want to say analyze topics, but really what it is pick up patterns and word distributions. It is a latent variable model. We'll get into what those are. There's only one use of it in journalism that I know of, and that was to, in another Reuters story, look at the topics of a bunch of court cases where, before the Supreme Court, to try to understand which topics were actually accepted by the court. So that's a very fast run-through of some of the things you can do with text analysis in a journalistic context. There's lots more, right? And people are inventing new ones all the time. But really, I show you that, we'll talk about it all more, but I show you that because I'm trying to motivate you to want to learn this thing that I'm going to try to teach you, which is the document vector space model. So now we're going to jump into a bunch of abstraction. And what I'm going to teach you is a thing called TF-IDF, which was used to do the clustering of message machine. And so what it's used for is to generate document vectors, which then can be compared with a distance function to decide whether two documents are, in this case, nearly identical. You can also ask questions like, do two documents talk about the same topics? This is also foundational search engine technology. So every full-text search engine uses something like this. Modern search engines will use lots of other parts too, but you can't really build a search engine without this stuff. There's a bunch of things that you can use TF-IDF for. Clustering we've seen. You can use it to try to extract keywords. You can use it to try to figure out the topics of things. It is a key part of every recommendation system that works with text, so Google News, Facebook Newsfeed, whatever. It's a standard method representation for doing document classification. So if you're running a classifier, you're running a classifier on vectors. You have to turn the text into vectors. And search engines are made from it. So here's the idea. We're trying to design a representation of a document as a vector, that is, as a series of numbers. In particular, as a series of numbers of a certain length. We more or less need all of our document vectors to be the same length for the same representation. So the simplest way we can start turning documents into vectors is by counting words. This is an ancient technique. People started doing this with the Bible in the 12th century. It's called a concordance when you do it with the Bible. And you can think of the counts as the numbers and the words as the dimensions, right? So this document has an 18 on the animal dimension. And so this complete set of dimensions is the set of vocabulary of all of the documents. So this is just word counts. You can also use word frequency, which is you just divide by the total number of words. And word frequency vectors or word count vectors are a fundamental representation which you'll use in lots of places. They are, of course, equivalent to a word cloud. Here is a word cloud with the same document. This is actually a press release from U.S. Senator Menendez of New Jersey. And, the reason people use word clouds is that it kind of tells you what the document is about. So, so what's this document about, just from the word cloud? Yeah, it's about enforcement of laws around reporting of animal cruelty. And there's this particular guy, Michael something, who was involved in dogfighting, and that's how it went. They made an example of him, I suppose. So the fact that word clouds can tell you interesting things about a document should convince you that word frequency can tell you interesting things. Notice that the doesn't appear here. They've removed it. Right? So that tells you that already we want to do something to the word counts. We don't want the raw counts. So here it is, just a little more formally, right? We're turning a document into a vector where each dimension is a word. And, here's a couple examples. This is what it looks like with two sentences. And you get this matrix. This matrix is called the term document matrix. An individual entry, which is denoted by term, it's indexed by term and document, is called term frequency. In this case, it's not actually term frequency, it's term counts. But divide everything, the first row by 3 and the second row by 1. Or 4. And you get term frequency. So this is the TF part of TF-IDF. One thing about this representation is that it is completely insensitive to word ordering. So if you have semantics that depend on the order of words, which is of course very common in language, then you're not going to be able to pick it up. It disappears in this model. This is why this is called the bag of words model. So you take all the words in the document, you throw them into a bag, you lose the ordering. This is less terrible than it seems. Before you can get there, you have to break it into words. That is more complicated than it might seem. So you're going to do some tokenization in the assignment after the next class. And the algorithm I've written there is really straightforward tokenization, right? It's about the dumbest thing you can do, and it'll work okay. There's lots of cases where this throws out information that you want. So, for example, punctuation, right? If you break words on punctuation, does that break don't into don and t? What about periods between the letters of an abbreviation, right? Is that going to break into, you have to break on periods because sentences end on periods. So more sophisticated tokenizers deal with punctuation. And in, Chinese, Korean, and Japanese, you don't have spaces between the word equivalents. And so tokenization is a completely different process. It actually becomes like probabilistic word splitting algorithms. Language is whack, is what I'm saying. You will find over and over that language is whack, I promise. Okay, so now we've got vectors. Now we want to get a distance metric. This is useful for a lot of things. So clustering, as we saw, matching a search query. So how a search engine actually works at the base level is it calculates the distance between every document and the search query, and then it sorts by distance and shows you the closest results. That's it. That's pretty much what a search engine does. Now, there's a bunch of other signals. Apparently, Google now uses 1,000 different signals or something. So the links thing, which is PageRank that they're famous for. Yeah, sure, all of that. But the most basic signal is, do the documents contain the word? And the documents don't have to contain the word, but is there enough similarity? So this is basic stuff. And the concept of the distance function we'll build is just overlapping terms. So we're going to build out something called cosine similarity, which is basically overlapping terms in document vectors. And you'll see why it's called cosine in a minute. There's different ways you could do this. You could use Euclidean distance to compare document vectors. So what I mean by that is, if I have a document vector, I have, so dimensions are words. It's always cats sitting on mats with me, right? So this is document 1, this is document 2, and I have, certain counts here, right? 2, 1, 3. There's a lot of cats and mats here. 1, 0. Then the Euclidean distance between these two documents is I take the sum of squares of the distances, right? So it's 2 minus 1 squared plus 1 minus 1 squared plus 3 minus 0 squared, and then square root of all that, right? So that's Pythagorean theorem. I can do this, it'll work. It has some drawbacks. Basically, the difficulty is that we need to normalize. Longer documents will end up being farther away from everything because they have more words. And so we'll get to what normalization means in a minute. But you can do this. It's not, it will work sometimes. But there's a standard thing that we use instead. And instead what we do is, instead of this Pythagorean formula, we take dot product. So that is to say, we change this. So instead of taking the squared differences, we do an element-wise multiplication and take the sum of those element-wise multiplications. Now, one thing to notice about this immediately is that anywhere where there's a 0, that term drops out, meaning that this takes into account how many words are overlapping in some way, right? So the dot product for any word disappears when that word only appears in one document and not the other one. And it's also, as I noted on the slide, it's not a distance function because this actually gets bigger when the documents are closer. So sometimes this is called similarity, and you can think of similarity as 1 minus distance. One of the difficulties here is that the longer the document, the more words that are in it, so these numbers get higher, or the more different words that are in it, the higher this gets for the same document, right? So if you think of comparing a document to itself, the longer the document is, the higher this dot product is going to get. And so this presents a problem. It screws up the similarity calculation. It just gives you clearly the wrong answer in a lot of cases. So which query do you think, or which document do you think the query should match here?
A.
Right. But it doesn't. Right, it matches B. So what we do is we normalize the documents. And the way we do that is we make the document vectors have unit length according to the standard L2 norm. Everybody know what I mean by the L2 norm? No? I'm trying to sort of calibrate where the math is. So there's different ways of measuring the length of a vector. One of the things you can do is just sum the absolute value of all the components. It's called the L1 norm. You can think of it as taking each component to the first power. Another thing you can do is you can sum the length of the squares of the components and then take the square root. That's called the L2 norm. You could also take each component to the pth power and then take the pth root. And occasionally you'll see that. It'll be like the L3 norm, or the L infinity norm, which if you think about it for a second, that'll just give you the maximum value. Anyway, it's the standard Euclidean norm that we're doing here, right? So we're dividing everything by the square root of the sum of the squares. And we're defining our similarity function, again, not a distance function, a similarity function, by the dot product divided by the lengths of these things, which, if you remember your vector geometry, is just the cosine of the angle between them. Conveniently, this also gives us a result between 0 and 1. So what does 0 mean here if I run this formula and I get a 0? What does that tell me about the documents? Okay, but linguistically? Yeah, no overlapping words. Right? What does a 1 mean? Yeah, they're identical. So the only way you can get a 1 is if A dot B is equal to the product of the lengths of A and B. And the only way that can happen, if you look at the formula, or you can either look at the formula for computing dot products, or you can think about the geometry of this. And the only way that can happen is if the vectors are identical. So now we've got a function that says 0 if they're completely different and 1 if they're completely identical. And so if we try this again, with all of this normalization going on, now we match the correct query. Right? We've matched A instead of B. So that's basically why we normalize. Is it's just it fixes this problem of longer documents for me. So here's a picture of what's going on. You can think of each of these document vectors as vectors in some space. Because all of the counts are positive, they're actually in the what is the word? It would be quadrant in 2 dimensions or octant in 3 dimensions, but the 1/2 to the n subspace of the high dimensional space where everything is positive. I'm sure there's a word for that. Anyway, hyperoctant. There you go. They're in the positive hyperoctant. And then we to match a document against another document, we look at the angle between them. And they're all normalized, which means actually you can imagine them as lying on a quarter circle in this picture. So after we normalize them, they're all going to be on a circle in 2 dimensions, or a sphere in 3 dimensions, or a hypersphere in the real world. And everything's on the surface of the hypersphere, and now we're taking the angle between 2 vectors on the surface of a piece of a sphere, the positive section of a sphere. And I tell you this because although you can always grind through the math, the easiest way to think about this stuff is to think about it geometrically. All right, your geometrical intuition will almost always give you the right answer. So then to turn similarity into a distance function, all we do is we say 1 minus the similarity. Right? So we went from something that is 0 when the documents are distinct and 1 when they are equal to something that is 0 when they are equal and 1 when they are distinct. And again, you can grind through this and show that it is a distance metric. So it's symmetric in A and B. When A and B are identical, it gives 0. And the triangle inequality is a little harder to show, but it basically just follows geometrically, right? So if I have 3 points on a sphere, then the angle from the first to the third has got to be at least as large as the angle from the first to the second plus the angle from the second to the third. And again, you can prove all of this if you're concerned about it. So that is cosine similarity or cosine distance. There are some problems if we do this on raw counts. And one of the big problems is that all of the common words are going to dominate the result. So actually, sometimes we want this. There is a case where we want this. So stylometry. So you're all familiar with the Trump Insider op-ed, which was that just last week, right? So a lot of people have wondered who wrote it. There is a classic statistical technique to figure out who wrote something. And the basis of that technique is to look at the frequencies of common words. The reason you use the common words, and compare to a corpus, right? So you need a bunch of different documents by a bunch of different authors, and then you compare the frequency of common words with the unknown document to the statistics of the authors. The reason you use the common words is because the common words are independent of topic, right? The authors might be writing about different things. Each author might have different topics. So if you start using words like, Iraq or something, then sometimes it'll match, sometimes it won't. But if you ask questions like, how often do you use the word which? Then you start to get results that work between different document sets. So sometimes this is what you want, but usually not. This is not what you want for a search engine or document cluster. What you would like is some notion of words that are distinctive. Words that appear in some document, but not others. And so the intuition here is that we're going to boost words that don't appear in very many documents.
Lodestar.
Right, exactly. Lodestar. I have my own theories about that. I think that document was
Calculated.
a deliberate pastiche. I think either it had multiple authors or it was built in part by cutting and pasting sentences from other places because they knew that everybody would do stylometry on it. Even so, I'm excited to see the first, it's coming. The first, maybe one of you can do it, right? But you got to be fast because it's going to be this week or next week, right? The first person to do a serious stylometry analysis on it, and I wonder what it'll say. And yeah, Lodestar is interesting, but what about the statistics of all the common words? So like, what happens if we apply the standard stylometry techniques? Although I will say that the statistical techniques are very useful and interesting and probably the most justifiable way to come to such conclusions. The Unabomber was caught by doing manual stylometry, like Lodestar style stuff. He had a particular phrase that he said that appeared in his master's thesis plus his manifesto. Anyway, so lots of history with stylometry. There's a People have done this for Shakespeare, for the Federalist Papers. There's a very famous statistical analysis that said that Madison wrote the anonymous Federalist Papers. Fun stuff. We want to downweight words other than the common words. Obviously, we want to downweight the, but we may also want to downweight car if we have a data set full of car reviews, right? But not if we have a data set that doesn't mostly talk about cars. So this tells you that the weighting function has to be a function of the entire document set and not just the individual document, because we want to vary the weights based on other documents. So about the simplest thing we can do is count document frequency. And so instead of counting how many times a word appears in a document, we count how many documents a word appears in. So and divided by the number of documents, right? We've got this, that's what turns into frequency, not a count. And I don't know, I mean, I guess I wanted to give you a formal definition, but it's not a very complicated idea. So I've done this like subset thing here. I don't know if that's particularly clarifying. It's the fraction of documents that have that word. And then we say, okay, well, we want to de-weight words that appear in many documents, so we're going to flip it, right? We're going to flip big D over the number of documents that contain it, and we're going to throw a logarithm in there because what the heck? Okay. I mean, the actual reason we need the logarithm there is we want a function that compresses the range, because we don't, so say we have a word that appears in 10 documents and a word that appears in 15 documents, or let's say 5 to 10. 5 to 10 is a pretty big jump. 90 to 95 out of 100 documents is not a big jump, right? So that tells us that we want more resolution in the lower end of the scale, where we have smaller numbers of documents. We want one additional document to mean more when it's not in many documents. So we're interested in relative or proportional changes, and applying a logarithm changes the scale so that an equal unit of IDF means an additional multiplicative factor of the number of documents that appears in. But guess what? We're totally making this up, and almost any function that compresses the upper end of the range will work. And by work, I mean give you search results that a human would pick. That's ultimately how this stuff was originally evaluated. So literally putting it together, we now have a function that tells us what value to assign to each dimension of a document vector, where again the dimensions are words, or terms as we like to say, as a function of the term, the document, and also the entire document set. Right, so notice that if I add one document to the set, it will change the TF-IDF vector of every document which contains any word which is in that new document. So it's a contextual calculation. Yes, which is what I'm saying here. Right, which is what we wanted. We wanted the importance of the word car to depend on, well, is this a corpus of car reviews, in which case we don't care, or is it, the AP News corpus, in which case, yeah, it should definitely be like, hey, this document is about cars. This has some interesting implications, by the way. This means that in principle, if we care about this type of idea, never mind the algorithm, if we care about this idea that the importance of a word depends on the corpus, then every time somebody adds a new document to the web, the search results for every other search should change on Google, which is actually true, right? Like, I don't know if it's true on sort of like a local scale, but it is definitely true that as the web evolves, Google's search algorithms will give different results for other searches. So now we are looking at TF-IDF on the same document, And notice that all the stop words have dropped out. Here is the word cloud again, right? So this is just straight word frequency. And here's TF-IDF. And notice that it's promoted some things, right? So Michael and animals are much bigger, right? Michael's relatively small here. It's relatively bigger here, and that's because the word Michael does not commonly appear in these press releases, right? And if you read the press release, turns out Michael's pretty important to this press release.
What was this data set?
Press releases from Senator Menendez.
All press releases.
Yeah, I mean, up to when I scraped it, which was like 2012. But it's like 5 years of press releases. Right, so Michael appears twice in this excerpt, which is not a very large number, right? Like, you know, all of the stop words appear more than that, and then animal or dogfighting also appears twice. Dogfighting doesn't rank. That's interesting. I think actually that's because dogfighting only appears in this document and no other, and the standard TF-IDF algorithm throws out. Yeah, this is kind of interesting, right? This is the practicalities of the stuff. You throw out words that don't appear in more than one document, and the reason you do that.
Isn't that a little misleading for Michael, at least, since Michael can mean different things, different people, different documents. Michael represents different entities in those different documents.
Yeah, but that's a different problem, right? So yes, so any word which has multiple meanings is going to have a hard time here. And actually, when we get to LDA, we'll look at one potential solution to that problem. But take a look at this formula. The IDF term, NTD, number of documents that the term appears in, if that's 1, then that's going to get a huge boost, right? We're going to get the log of the total number of documents. So that term's, you know, it should match perfectly. The problem is that if we're trying to cluster documents, which was what I actually built that algorithm for when that generated that TF-IDF data, that term can't match any other document, right? If dogfighting doesn't appear in any other document, then it can never contribute to the cosine distance of another document. So for a search engine, you might not want to do that. For clustering, it actually cuts down the data quite a bit because there's lots of words that only appear in one document. Anyway, that's TF-IDF. This stuff is from the 70s. A guy named Sultan did a lot of work on this. This is like foundational search engine stuff. And this is how he drew it. He said that, you know, we would like the document vector space to have these little clusters. And we want the clusters to be documents that are about the same thing. In fact, there's a formalization of this called the cluster hypothesis. Here are some actual multidimensional scaling plots of 2 sets of document vectors, the TF vectors and the TF-IDF vectors. The colors are manually assigned topics. They are me going through and tagging this, and we'll see the tagging interface a little bit later. I guess next class at this point. If you look at the TF side, what you see are these sort of long sort of streamers. I see one that's sort of going sort of to the upper left, and I see one that's sort of going almost straight up. And then a big central blob in the middle. And what's happening there is that those sort of linear dimensions, that's the projection of the stop words, right? So one of those things is the dimension. And our space is really warped by just the shape of how common those words are in English and how common they are in the press releases, right? Some of these dimensions are going to be the there's going to be the Menendez dimension, right? Because they all have his name in it. There's going to be the like appeared dimension, or I don't know, whatever it is that politicians say most commonly. And then that central blob in the middle is kind of everything else. And so we don't get very clear separation of the clusters. When we divide the term frequencies by IDF, we cancel out not only the stop words, but the Menendez style stuff. And we get much more distinct clusters, as you can tell from the fact that many of those topic clusters are now much more compact and distinguishable. All right, so that's why we do this. There is an interesting assumption here. It's an assumption which is empirical in nature. The cluster hypothesis has appeared in various forms since people started doing this type of like search engine algorithm design. Like this dates from the earliest days of TF-IDF, and even earlier actually. There's sort of proto versions of this from the 50s. And it says that this algorithm of turning things into a vector space, like this word counting thing, tends to put semantically similar documents together. Or in this case, they say behave similarly with respect to information needs, right? If you're building a search engine, but we do all kinds of things. We're gonna look at document clustering, and we're gonna look at like keyword analysis and all kinds of stuff. And the underlying assumption of all of this stuff is that the clusters in this space mean something. Now, you can't prove this from the mathematics. And in fact, the TF-IDF formula is not really that important. There's dozens of variants. And one of the references in the syllabus goes through like what some of these variants are. And different search engines and different packages will give you different answers. It doesn't really matter. They all kind of do the same thing. They all kind of work on the same intuition. And I want to point at this because in almost all of the work that we do, there is some sort of often unspoken hypothesis of this type, which connects the semantic and the mathematical worlds. So I talked about the connection between the words and the data. The only way that happens is by introducing a hypothesis like this. And to the extent that the hypothesis is correct, then the statements that you write about the data have empirical meaning. Right? So there's something going on in the background here. And also TF-IDF just works, right? You can build useful search engines with this. Anyway, there's poor theoretical justification for it, but it empirically it works pretty well. This idea, not just TF-IDF, but the idea of encoding documents as word vectors in some fashion, most commonly in a TF-IDF-ish type of way, is called the vector space document model, and it is foundational to all types of text analysis, including the text analysis that is built into Overview.